We present a framework to integrate secondary motion into the existing animation pipelines. Initially, a rest pose and its animation sequence is given. The user determines the bones to be simulated as mass spring systems and the simulation parameters. Then, our pipeline automatically computes the secondary animation. Our method achieves secondary motion for a wide range of subjects. Unlike common approaches, we do not directly simulate the mesh vertices, hence, we do not require a volumetric mesh. We only simulate a small number of bones. Complex surface dynamics are approximated with a linear combination of spring motion. To localize the jigglings, the user can also augment additional bones to the input rig. Our method can also be used to inject dynamics on a blend shapes deformation. The blue bones are the augmented spring bones to the input rig. Here, we keep the same augmented rig to obtain the secondary motion for an entirely different animation. We compare our method against another finite element method with a tetrahedral input. Notice the tetrahedral simulation in the middle can introduce unwanted dynamics in the cow's legs. The point handles in our case exaggerate the rocking motion of LBS. Here, blue helper bones localize the jiggling around the ears and the trunk. Notice the detailed rig explodes for the tetrahedral simulation in the middle. Skinning of tetrahedra self-intersects when simulated bones are too close, causing edge springs to explode due to time stepping. Our method avoids such problems of tetrahedral skinning. We also compare our method against fast complementary dynamics. On the left, the duck model is tetrahedralized and a single handle is attached. Next, we input a complete rig. Notice for complementary dynamics, the duck becomes too stiff as we increase the number of bones, whereas our method allows local control for secondary dynamics. Note that some models are poorly tetrahedralized. Our method can work on shell meshes, avoiding such problems. Our kinematic constraints are essential to produce plausible rig dynamics, even in the unstable case. The user can adjust the spring parameters for different dynamics. Here, a higher stiffness value returns to the rest shape faster. The user can also adjust spring rest length along the bone. At the extreme, a zero length spring at the bone tip achieves different jiggling dynamics.